so what we're going to look at in this next example, we're going to actually revisit the previous example that we did, but we're going to throw another word in there. So we're going to get another definition here first. So events are called mutually exclusive. It should be underlined. Mutually exclusive when they have no outcomes in common. In other words, it's impossible for both events to happen at once. Right? When two sets have an empty intersection, they are called disjoint. There is no overlap between the two sets. So if we look at this, this would be a picture of an example of two disjoint sets. And the reason that this matters is this is going to affect the way we find the answers to our OR probabilities that we just looked at. So down here we have probability rule number 4. The probability of A or B equals the probability of A plus the probability of B minus our probability of A and B. This subtraction eliminates the possibility of an event being counted twice. Or if A and B are mutually exclusive, right, so this rule 4A is just if they are mutually exclusive, then our probability of A or B is just going to be simply the probability of A plus the probability of B. Right, so understanding mutually exclusive, being able to decide whether or not two events are mutually exclusive is going to be key to us in our different ways of finding our OR probabilities. So we're going to go back to the last example that we just looked at, where we were comparing education and marital status, and we're going to include this idea of mutually exclusive, and then kind of go from there. So same table that we've been looking at for all the rest of these problems. So use the table to decide if the events are mutually exclusive, and then find the probabilities below. So the person is married and the person is single. Right, so if we look at this, we have two different columns here. Right? It's impossible for a person to be in both columns. It's impossible for a person to be both single and married at the same time. So in this case, we would say mutually exclusive. It is impossible to be both. So it's impossible to be both. All right, so to find our probability, right, what we did before, right, in our table, we took our 112 plus our 408. Right, so since these are mutually exclusive events, we can use formula 4A, which tells us that we're going to find the probability that someone is single plus the probability that someone is married. There's no subtraction needed here. Okay. So the probability that a person is single, well, that's 112 plus 408 divided by 665 gives us 520 out of 665, which gave us our 0.782 or 78.2%. This is exactly the same as what we saw before. Right? So we'll just say here, same as before. Same exact calculations and everything. All right. Now, if we think about our other example was talking about whether a person is married and has a college degree, right? These are not mutually exclusive. It is possible to be both. Right? So what that means is this time around for our formula, right, we're going to do probability that a person is married plus the probability that someone has a college or higher level of education minus our probability of M and C. Okay. All right, so we are going to take these. We have 408 the people that are married. We have 143 that have a college education. And then we're going to subtract this 98, because that's the number of people that are both. And we're going to divide that by 665. Right. That is going to give us 453 out of 665, which is 0.681 or 68.1%. So slightly different calculation, but same answer as before. Right, and more often than not, this is going to be the way that we're going to choose to do these, because a simple adding two numbers and subtracting one is generally going to be a little bit faster than adding up a long list of numbers, as we did in example B of the previous example. So when you're finding OR probabilities, pay attention to whether or not your events are mutually exclusive, and then be sure to find those probabilities accordingly.